You want one of these? Okay. All right. So those of you who are in my class, we are going over notes. We're going over notes today. So the first thing we're looking at is this here, the fundamental theorem of algebra. Now, the fundamental theorem of algebra we will look at, but we're going to look at this table here first. This table here shows us four different equations. Now, the first equation we have is 2x minus 1 equals 0. Now, if we solve this equation, which is a degree 1, because the biggest exponent attached to a variable is 1, we have a solution of 1/2. Now, the number of solutions that we have is 1, because it's just 1/2. Now, the second equation we have is x squared minus 2. Well, the degree is 2, because the biggest exponent attached to a variable is 2. If we solved it, the solutions would be plus or minus the square root of 2, giving us a total of 2 solutions. Next one we have is x cubed minus 8 equals 0. Since the degree is 3, because of the biggest exponent, the solutions, if we solved it, would be 2, negative 1 plus I squared to 3, and negative 1 minus I squared to 3, giving us a total of 3 solutions. And lastly, our x cubed plus x squared minus x minus 1 equals 0 is also a degree 3, giving us solutions of negative 1, and 1. We have 3 solutions there. And what this leads to is a fundamental theorem of algebra. And it states if f of x is a polynomial function of degree n, where n is greater than 0, then this equation has at least one solution in the set of complex numbers. Well, all that tells us that even if x is equal to 2, that is our solution. I can say plus 0i, it's in the complex solution. We can add 0i to it, it's now a complex solution. That's not the big piece. The big piece is the corollary. What is going to come from that there? Is that if a polynomial function of degree n, where n is greater than 0, it has exactly n solutions, where n is the degree, provided that each solution that is repeated is counted each time that it's repeated. So if a solution is repeated twice, it's counted as 2 solutions. If it's repeated 3 times, it's counted as 3 solutions. Now that is helpful because when we start looking at polynomial functions, we can know how many solutions the polynomial function should have. So if we look at this first example here, how many solutions does the equation x cubed plus 3x squared plus 16x plus 48 have? So how many solutions should that have? 3. It'll have 3 because the degree is 3. If we look at this next one here, x to the 4th plus 6x cubed plus 12x squared plus 8x. How many solutions should this one have? 4, because the degree is 4. It has 4 solutions because the degree is 4. Those solutions for this actually are negative 2, negative 2, negative 2, and 0. We do have negative 2 repeated 3 times, so we count it 3 times, and 0. All it asks is how many zeros does it have? It has 4. Let's look at this one here. X to the 4th minus 2x cubed plus 5x plus 12. How many solutions does it have? 4, because the degree is 4. How many solutions should this one have? 3. So this one will have 5. Now, unfortunately, unlike the last few, it didn't actually ask us how many it had. It's actually going to ask us to find them. Now, for this one here, the first thing I would do, especially finding these zeros, is to grab the graphing calculator and graph it. We're going to graph it and see how many zeros we have. So we're going to plug it in as x to the 5th plus x to the 3rd minus 2x squared minus 12x minus 8. and we're going to hit graph. Now we see that it intersects the x-axis at two spots. There's two locations where it's going to cross the x-axis. Now, one thing that is interesting to note is that at -1, at that -1 location, it does not cross the x-axis. Let's focus in, guys. You focused? Okay. Where at that -1 spot, because it intersects the x-axis but does not cross it, has what we call an even multiplicity. There's an even number of zeros at that spot. So the number of zeros that could be there is going to be 2, 4, 6, 8, 10, 12. It could be those numbers. It's not, because the degree is 5. We can have at most 5. And at 2, we also have 0. So the two solutions that we know for sure is that x equals 2 and x equals -1. And we're hoping that -1 is going to repeat at least once. Because the minimum number of zeros that we need to have for this here is 3. If we have 3, we can get it down to a quadratic and solve from there. If we got 4, that's linear. If we have 5, we are finished, because that's every solution that we could possibly have. So we put the numbers across the top. For our synthetic division, we'll have 1 for x to the 5th, 0 for x to the 4th, 1 for x cubed, -2 for x squared, -12 for x, and -8. We bring the first one down. We can use 2 first. Now we're going to do our multiplication and addition steps. So we're going to do 2 times 1, which is 2. And then we're going to add straight down. 0 plus 2 is 2. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. -2 plus 10 is going to be 8. 2 times 8 is 16. -12 plus 16 is 4. 3 times 4 is 8. And -8 plus 8 is 0. And that is what we wanted to have happen. Now the other solution that we have is -1. So we are going to use it here and do the same process. So we'll have -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. 5 plus -1 is 4. -1 times 4 is -4. 8 plus -4 is 4. -1 times 4 is -4. And lastly, 4 plus -4 is 0. Now we are going to do this one more time because we really want -1 to repeat itself. Since it did touch the x-axis but did not cross it, we're hoping there's a repeated 0 here. And if that remainder is 0, then that is a solution twice. We have it now down to a quadratic. Now our -1 times 1 will give us -1. Now our 1 plus -1 will be 0. Our -1 times 0 is going to be 0. 4 plus 0 is going to give us 4. And -1 times 4 is -4, and 4 plus -4 would give us 0. So it does indeed work that -1 showed up twice. It is a 0 twice, which was the third solution that we needed. Now we're just looking for the last two in the remaining expression in this remaining equation. So at this point here, we do need to fill our variables back in. 4 is going to be our constant term. It's going to be the number without x. 0 is going to be the term with x, and 1 is going to be our term with x squared, telling us that the final expression that we have for this here is x squared plus 4 equals 0. Now this equation is nice in that we don't have a middle term. We don't have x to the first, because if we did, then we're going to have to use quadratic formula completing the square. Without that middle term, we can actually solve this using the square root method. And the square root method just tells us we get the term being squared by itself. And the first thing we need to do to get x squared by itself is just subtract 4 from both sides. At this point here, x squared is by itself, which means we can take the square root of both sides. Our square root and squared cancel, giving us x by itself. Whenever we take the square root of both sides, we have to put the plus or minus. So we have x equals plus or minus, well, the square root of negative 4. The negative is going to come out as I. Square root of 4 is 2. Telling us that our last two solutions are plus or minus 2i. So on a whole, our solving steps and how we go about solving it really isn't changing from what we did earlier and what we did yesterday. It's just now we have complex terms instead of just irrational terms. Questions on this here? Let's look at this next one here. We have x cubed plus 7x squared plus 16x plus 12. So because of the fundamental theorem of algebra, we know that this function, this equation should have how many zeros? It should have 3. So let's go on and graph it and see what it tells me. X cubed plus 7x squared plus 16x plus 12. So we do see that it crosses and intersects the x-axis at least twice. And one of those two spots, it looks like it might be negative 2, intersects or touches the x-axis and goes back up. Negative 3, we can definitely see it does cross there, so it does have an odd multiplicity. Odd multiplicity shows up an odd number of times, so it could be 1, 3, 5, and going on, but that's not the case here. So we know for sure x equals negative 3 and negative 2. Now the reason I'm saying negative 3 cannot have an odd multiplicity is because it's either going to show up once or 3 times. But the degree of this function is 3, so there should only be 3 solutions. If it showed up 2 more times, that would actually give me a total of 4. That's way too many. Now, negative 2, it can be, it looks like it might be possible that it is a repeated solution. It shows up twice. But it was kind of a little, at least on my screen, probably on y'all's, it was a little fuzzy on telling, did it actually cross at 2? Or did it bounce off the x-axis? But luckily, for us here, we did get the minimum number we needed. We needed at least 1. We did get that. And now we can do the synthetic division, simplify it down, and see what our last solution is going to be. Do we want to use negative 3 or negative 2 first? Doesn't matter. Negative 2. And we're going to go through this process again. Negative 2 times 1 is negative 2. 7 plus negative 2 is going to give us 5. Negative 2 times positive 5 is negative 10. 16 plus negative 10 is 6. 2 times 6 is negative 12. And 12 plus negative 12 is 0. Now at this point here, we could try negative 2 again and see if it does bounce off that graph and is repeated 0. But is there really at this point a guarantee that negative 2 is going to work twice? Not really, but do we know one that does? The negative 3. Because there's nothing saying that we can't try negative 2 again, but if we do and don't get 0, we've got to erase all that and restart it. We know negative 3 works for sure. Negative 3 times 1 is negative 3. 5 plus negative 3 is 2. Negative 3 times 2 is negative 6, and 6 plus negative 6 is 0. And it is looking like the setup here is telling us that the other x value is -2. Because at this point here, we can plug our variables back in. We do have our remainder. The 2 is our term without x. 1 is going to be the term with x, telling us that x plus 2 is equal to 0. And finally, to solve this, we would subtract 2 from both sides, telling us that x is equal to -2. So it did work out that at -2, the graph did bounce off the x-axis, giving us that repeated 0. Questions on this here? All right, we're going to look at this last one here, and then we'll move on to the next piece. The last one we're solving for today is f of x equals x to the 5th minus 3x to the 4th plus 5x cubed minus x squared minus 6x plus 4. And again, the first thing I would do is graph it. X to the 5th. 4. So we're going to graph this here, and we do get this graph. This is what we should be looking at. Now, if we go second table, again, we need to find the values of x that is going to make this function equal 0. Now, one of the ones that we find is -1, because when -1 is our x value, the y value is 0. And when x is 1, it is also 0. Now we know we need 3 values. If you notice, it looks like the graph touches the x-axis at +1, but does not cross it. So there's a good chance that 1 is being repeated more than once. Now again, it doesn't matter which one of the 2 values we use first. I'm going to pick -1 to do our synthetic division, and we know it's a solution, so we know that the remainder is going to have to be 0. So the first thing we're going to do is our multiplication. -1 times 1 is -1. Then we're going to add straight down. -1 plus -3 is going to be -4. -1 times -4 is now +4. 5 plus 4 is 9. -1 times +9 is -9. And -1 plus -9 is -10. -1 times -10 is going to be +10. -6 plus 10 is 4. And lastly, -1 times 4 is -4, and 4 plus -4 is indeed 0. Now at this point here, we're going to repeat this process with +1. Now 1 times 1 gives us 1. -4 plus 1 is -3. 1 times -3 is -3. 9 plus -3 is 6. 1 times 6 is 6. -10 plus 6 is -4. 1 times -4 is -4, and 4 plus -4 is indeed 0. So we do have those 2 solutions. And again, if we go back and look at the graph, at +1, it looks like it touches it but does not cross that x-axis. So there's a good chance that +1 should work a second time. And we do our multiplication again. 1 times 1 would give us 1. -3 plus 1 is -2. 1 times -2 is, well, -2. Six plus -2 is 4. 1 times 4 is 4, and negative 4 plus 4 is 0. Questions on this so far? Now, based off the graph, it could be possible that we do have another solution at 1 or negative 1. If it's at negative 1, because it crossed, it would have to show up 2 more times to keep that odd multiplicity. The same thing with positive 1. For it to keep that even multiplicity, it's got to show up 2 more times. And looking at what we have left, if we put the variables back in, we would have x squared minus 2x plus 4 is equal to 0. One and negative 1 are not going to be factors for this here, because they would both have to be 1 or negative 1, and 4 factors of 4 wouldn't work because, well, let me take a step back. If it is 1 or negative 1, this would have to be factorable, because they're rational solutions. Rational solutions for a polynomial expression are factorable, and 4 factors do not contain 1 and 1. It's 1 and 4 or 2 and 2. So both of those options are out. Now, square root method is out too, which means it's either completing the square or the quadratic formula. I'm just going to default, we're going to use the quadratic formula. There's nothing wrong with completing the square. I just think it takes a little more time to do completing the square than it does the quadratic formula. Now, the first thing we're going to do is plug in the values of a, b, c. A is the number in front of x squared. Well, our number in front of x squared is not written, so it's understood to be 1. 1, yep. It would be, if it was 0, we wouldn't have a term there. Because 0x squared would just be 0. Our next number is our value of b, which is negative 2, and we're going to plug it in its 2 spots there. And lastly, c is positive 4, and we're going to plug it in its 1 spot. Questions on how we plug this in? Now, at this point here, we need to simplify. Negative 2 is going to become positive 2. In the bottom of the fraction, we have 2 times 1, which is just 2. Now, the last thing we need to simplify in this here is our negative 2 squared minus 4 times 1 times 4. And at this point here, I would just grab a calculator and say negative 2 squared minus 4 times 1 times 4 and let the calculator do it for us. And it tells us that it is negative 12. Now, the 30xs will simplify most radicals for us. It just will not simplify negatives. It will not take the square root of negative 12. However, we do know that that negative is going to have to come out as odd. So really what we're doing is not looking at square root of negative 12, but more looking at I square roots of 12. Now the calculator, the 30xs, will take the square root of positive 12, which is 2 square roots of 3, which means for us that the square root of negative 12 should be 2i square roots of 3. We just have to take that kind of in-between step. And at this point here, we can say this is the final answer as long as those top two numbers do not have a common factor with the number on bottom. As long as 2, 2i, and 2 do not share a common factor. And well, they actually do. They all share a common factor of 2. Now, we can divide 2 out of all 3 spots. I look at the denominator first. 2 divided by 2 is 1. So the denominator is going to simplify out completely. So this 2 is going to simplify out completely. Our first 2 divided by 2 is 1. 2i divided by 2 is just going to be I. And we still have our square roots of 3. So that tells us that the final two solutions are 1 plus or minus I squared of 3. So 1 plus I squared of 3 and 1 minus I squared of 3 would give us all 5 of our solutions. Questions on this here? We have 2 theorems left before we're finished with this chapter. And that's one here is our complex conjugate theorem. Complex conjugate theorem states if A plus BI is a solution, then A minus BI is a solution. If we have one, we have to have the other. They always come in pairs. Now, in years past, we've done this here. This piece here is just like what we were doing yesterday. And it told us to find, or we're trying to find a polynomial of least degree that has solutions of x equals 2 and x equals 3 plus I. Well, if x is equal to 3 plus I, it also means it has to equal 3 minus I. And we would set them equal to 0. We'd multiply them together. We would go through this whole process. But I'm going to be nice, and we're going to skip that and go to our final theorem. And that's Descartes' rule of signs. Now, Descartes' rule of signs is helpful in that it tells us the number of possible positive zeros and the number of possible negative zeros, or less than it by an even amount. So it'll tell us the maximum number of possible positive zeros we can have, number of possible positive negative zeros we can have. It gives us a better idea of the function. Now, the way we determine this for positive, our number of positive zeros, is we take the function itself and count the number of sign changes from term to term. If there are any terms missing, we don't care. We just count the sign changes of the function itself. So as we look at this here, from x to the 6th to x to the 5th, did the sign change? Because we're going from positive to negative, so there's 1. From x to the 5th to x to the 4th, did the sign change? Yeah, so that's 2. X to the 4th to x to the 3rd? Yes. X to the 3rd to x squared? No. X squared to x? No. X to our constant? So how many times did the sign change across there? 3, yes? So the number of possible positive zeros we could have is 3 or an even number less than. So we really could have 3 or 1. Any questions on how we found the number of possible positive zeros for this function here? We're ready to find the negatives. To find the negatives, we do almost the exact same thing, but we have to do it for f of negative x, which means we have to replace every x in f of x with negative x. So the first thing we have to do is replace every x in f of x with negative x. We are going to have to simplify all this down because we can't just leave it as negative x inside those parentheses, because we need to see how the sign's changing and then count our sign changes. Questions on this so far? Now, I'm going to look at this term first. You don't have to write this. But x, or negative x to the 6th, really says we're just taking negative x and multiplying it by itself 6 times, yes? Because that's really all it's saying. Negative x to the 6th, we're multiplying it by itself 6 times. Well, we're going to ignore the sign for now. X times x times x times x times x times x. If I multiply x by itself 6 times, it is indeed still going to be x to the 6th. Would we agree with that there? So really, is the exponent for any of these going to change? No, the exponent's not going to change because it's still the same number of x's. The main thing we're focused on is, or the main thing we need to focus is on that negative sign attached to x. When we multiply x times x, it's going to become positive, yes? When I multiply that positive by the next negative, it's going to be negative. That's going to have to move. And when I multiply it again with the negative, it becomes positive. So when I multiplied two negatives together, it made a positive. When I multiplied it with that third negative, it became negative. Fourth negative, it became positive. Fifth, it goes back to negative. And sixth, it goes back to being positive. And that should be interesting because anytime that amount was even, the sign is positive. Whenever the exponent or the amount that we multiplied it by was odd, it ended up being negative. So with this here, with our x to the 6th, it is still going to be x to the 6th, but that negative is going to become positive because we multiplied it by itself, that negative by itself, an even number of times. So we know if the exponent's even, that sign should be positive coming out of that parentheses. If the exponent's odd, it should be a negative coming out. So if we look at negative 2 times x to the negative x to the 5th, now the x to the 5th will still be x to the 5th. But we do now have a negative coming out because of it being an odd power, which means that 2 is going to change from negative 2 to positive 2. Let's focus in, guys. So really, our negative 2 times negative x to the 5th is going to become positive 2x to the 5th. Our next one, our negative x to the 4th. Again, the biggest thing, if that exponent is even, keep the sign. If the exponent is odd, we change the sign. Here, since we're talking about x to the 4th, x to the 4th is even. So it means our positive 3 is going to stay positive 3. Our next one we have is going to end up being 10x to the 3rd. But because that negative x is being put to an odd power, it means that sign attached to the 10 is going to have to change from negative to positive. Our next one is going to end up being 6x squared. But because the exponent's even, the sign is going to stay negative. If the exponent's even, the sign stays the same. If the exponent's odd, we've got to flip it for this negative x power. Now the last one, it's not written, but the exponent's understood to be 1. So it is an odd power, so the sign is going to have to change. Also, since it is just x to the 1st, well, negative 8 times negative x is going to be positive 8x. And our constant term did not have a variable attached to it, didn't have a negative x we put into with it, so it's just going to stay negative 8. Now, we need to count the sign changes. Well, x to the 6th, from x to the 6th, x to the 5th, there is no sign change. From x to the 5th to x to the 4th, there's no sign change. X to the 4th to x to the 3rd, no. X to the 3rd to x squared, there's 1. X squared to x is 2, and x to our constant term is 3. So the most possible negative 0 we can have is 3. So the maximum number of negative solutions we can have is 3, or an even number less than it. So we can subtract 2 from it, get 1. If I subtracted 2 again, we would get negative 1. I cannot have a negative number of solutions. So 3 and 1, 3 and 1. Questions on how we found the possible number of positive solutions and the possible number of negative solutions? Are we ready to actually write the answer? So the answer for these here is going to come in the form of a table. Because we can have positive solutions, we can have negative solutions, and we can have complex. Complex is not listed in either of the two because all of our complex solutions, when they do show up, we do not cross the x-axis, so they cannot be considered positive or negative. Now, how many positives did we say we had at most? 3. And the most negatives we can have is 3, yes? What's the degree of this function? 6. So if I have 3 positives and 3 negatives, am I missing any? No, because they're all there, which means the number of complex solutions that we should have is 0. All right, guys, questions on how we set this up so far? Now, the way I approach this, once I put the max number in both of those spots, I start subtracting 2 from the negatives till I can't. So we can take one group of 2 away from the negatives, which tells me that I can have 3 positives and 1 negative, yes? Which gives me a total number of, how many are we supposed to have? How many am I missing? 2. Since we're supposed to have 6 and I only have 4, that means 2 of those remaining 2 I'm missing, have to be complex. And I take another group of 2 away from the negatives. Whenever I can't take any more groups of 2 away from the negatives, I reset it back to the maximum that it can be and take one group of 2 away from the positives. And then repeat that process. I keep taking groups of 2 away from the negatives till I can't anymore, reset it back to the max, and take 1 away from the positives. If I hit a point where I can't take any more away from the positives, we're done. Because now we could have 1 positives, 3 negatives, still missing 2, because that's total 4. So take another group away from the negatives, telling us that we can have 1 positive, 1 negative, and so that there is the solution set, or that's the solution for this here. Because this helps us, especially with the rational zeros theorem, to start eliminating possible solutions, possible outcomes that we could have, so that we have a better idea of what zeros to be looking for. We've run out of time. We will do probably 1 or 2 more of these tomorrow, but this is really it with chapter 4.6. I did put the assignment on the whiteboard. I did put it in Google Classroom, because for the rest of it, you should be able to get knocked out. We're going to do 1 or 2 more of these tomorrow, but this is it of chapter 4.